Hello, I've only recorded part of the lecture today, part of the things that I thought were the most important. So let's go through this. Um, okay, the exam, the second and last exam will be 2 weeks from today. It'll be on magnetoelectronics, optoelectronics, and digital electronics. Okay, I just showed a few things on Minecraft computers. Somebody here used, in 800 hours, they made a Minecraft computer, a 32-bit calculator that did addition, subtraction, multiplication, division, and square. So I looked at the first 1 minute of this, and 16-bit Minecraft computer, the first 2 minutes of that. Okay, the computer refers to an object that has accepts some input and produces some output. And I showed sand to silicon, making chips from the silicon and sand. And we looked inside the Google data center the first minute, and from basically 3 minutes to 5 minutes, which showed how Google data centers work and how much heat they produce and how they have to cool them. And basically they're made of hard drives that you'd find in your desktop computer. Okay, we showed how you can take many NAND chips and made other chips out of them. This is call us a circuit if we have more than one chip. And why NAND gates? And NAND gates are smaller, cheaper, and faster. So almost all the gates you have in your phone or computer are made of NAND chips, not AND. I showed how you use a full bit adder that works on each set of least significant bits here, A and B of a number. A is a number, B is a number, and gives out S, an answer, and a carry. Each one of these adders does that. 2 bits in, a carry in, a sum out, and a carry out. And multiplication is much like digital multiplication. You multiply, it's like 11 and 14 in digital are these binary numbers, and how you multiply 0 times this one, a 1 times this and move it over 1, 1 times this and move it over 1, and then just add the things and you get the right multiplication. And here's a 2-bit by 2-bit multiplier. Mini terms. This basically shows you how you can turn a light bulb on from one of 2 switches. Switch in a room that has 2 doors, and a switches by each door. You can turn on and off a light by either switch. So we represent this as a matrix. We're calling this A input and this B input. And if it's up, it's a 1. If it's down, it's a 0. Up is a 1. Up is a 1, and down is a 0. And you get a light when they're both down or both up. And we call what we get, the answer we get out is a mini term. And we're only considering when we get a 1 out. We're not going to worry about what we get with a 0. We're just going to forget about that. But here we have 2 mini terms. Wherever you get a 1 out, it's a mini term. You can write down the Boolean expression for each. 2 zeros, that's A bar, B bar. And if you have both of them on, you have A and B. A times B is a 1. So then the whole equation is A bar, B bar plus A times B. And the plus is an OR. And the multiplication is an AND. And here's an XNOR chip. Basically, will do what this does. You have more complex circuits. Here you have 3 inputs, A, B, and C. You get 3 mini terms out in different rows. And you can get you see this one out here. You have to have A times B times C bar. A, B, C bar. And so each one of these mini terms is going to give you a term in the equation for the output. And then you can simplify these things. Here, B bar, C bar, B bar, C bar is in both, so you can factor out the A and you can factor out the B bar and C bar and get A plus A bar times this, and A plus A bar. So it says that you can have an or, either or 1 or a 0. So that's always a 1. That's always a 1. So then you can get rid of one of the inputs on that term. And I showed the first minute or so of a simplifying an equation. Okay, now we come to Carnot maps, geographical solutions that greatly simplify truth tables. So we want to take this A, B, C, D, have these 4 inputs, and you get 4 outputs, 4 mini terms here. And you can compress that into a 4x4 table. You have to order the rows and columns in a certain way. I'll show you that. A and B here in this column would be A bar, B bar. Anything in this column would be A bar, B. In this column would be A, B. And in this column would be A, B bar. And then the same with this. So we have four mini terms here. But you can compress this. Normally we'd get 4 terms in the equation for the output, and each one of those would have 4 inputs. And we want to simplify that. And here's what we do. Okay, we can write the whole equation. Here's 4 terms for the output, and each one of these has 4 inputs. Pretty complicated, right? And then you can simplify it a little bit. But you can do that with a truth table and the Carnot map. Okay, so what you notice is here you have 2 adjacent mini terms. Whenever you have adjacent mini terms, notice that these 2 adjacent mini terms, you have to have an A, because A is 1, so that's A. But B can be 1 or 0. B can be 1 or 0. That means B is going to drop out of the equation. And that's exactly what happened here. You have A, no B for these 2, and C bar D. A, C bar D with no B in it. That's because you have adjacent terms. Okay, before you set this table up, you have to use these matrix rules. That when you set up the individual boxes here, you have to increment only one of the digits. Like from 0, 0, I go from 0 to 1, 0, 1. Now, I can only change one of these digits, so I'm going to go from, I don't want to go change 1 back to 0, because that'd be the same thing as this. I want to change this 0 to a 1 in the adjacent column, so I get this 1 to 1. And then I don't want to change this 1 to a 0, because I'd go back that way, so I want to change this 1 here to a 0. So I have all 4 possibilities, 0, 0, 0, 1, 1, 1, 1, 0. But each time you go to an adjacent column, you're only changing the index, the bit, by 1. That's very important when you set this up and the CDs up. Okay, so this mini term corresponds to A bar, B bar, C bar, D bar. Okay, this one here would correspond to A, B bar, C, D bar, since it's in here. Okay. So when you combine these adjacent rows, you find that B drops out and you get this equation, and it's the same equation as you did if you did it by hand this way. But when you have more complicated truth tables, then it becomes more time saving. Okay. Okay, so the rules are you have to order the top axes and the side axes a certain way. And now you want to group even numbers of ones, like these two ones. Well, let's go back here. These two are adjacent, right? In this example. So it doesn't matter what D is. D can be 1 or 0, so D is going to drop out. D is going to drop out. And here's an important thing now, that it didn't matter where I started. I started here at 0, 0, and I went this way. But I could have started the 4 columns and starting from 0, 1, 1, 1, 1, 0, 0, 0. So instead of using this, 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 and this, these 4 columns, I can use this, 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 and this, and you get the same answer. So what that's doing is saying I'm taking this edge here and wrapping it around to this edge here. So this column basically is transported over to this column. So originally what I had was a mini term here and a mini term here, and it didn't look like they were adjacent until I took this column and put it over here. I wrapped it around. Now I have 2 adjacent ones, mini terms. So now I can get rid of, you can see that A can be either 1 or 0. So A is going to drop out for these two. B has to be B bar, and C has to be C bar, and D has to be D bar. Okay. So the first thing you do is order the tops and sides. Then you find groups of even numbers, ones that are adjacent. And you can wrap around this cylinder. And I'll get to that. Each group is 1 mini term. If input is both 0 and 1, you don't need that input. That drops out. So the first column of adjacent ones here, D dropped out. Here, A could be anything, 1 or 0, so A dropped out here. And so here's your 3 terms. So instead of having 4 terms, 4 complete terms, and each one of those terms having 4 inputs, I now have 3 terms. I've gotten rid of one term, and 2 of the terms only have 3 inputs instead of 4 inputs. Here's one with 4 inputs, 3 inputs, 3 inputs. There's some. Okay, so here's the problem, 20, number 1. We're going to solve for y. So you have A, B, and C, and when you have a certain A, B, and C, you're going to get a value of y. So y is equal to the number ABC. So here you have A and B here. This would be A, this would be B, or this would be A bar, and this would be B bar. And this row here would be C bar, and this row here would be C. Okay, so you can, these are adjacent, so I can wrap these together. It doesn't matter what C is, so C is going to drop out. And this will be just A bar, B bar, A bar, B bar. Now, I can take this one and combine it with this one because I can wrap it around. I can take these 8 squares here and wrap it around here and start from any position so that you see that this one and this one are going to be adjacent. Okay, so you know that it has to be C. And then what happens with A and B? Well, you have to look up here and see A is 0 here and A is 1 here. So A can be either 0 or 1, so A is going to drop out. And then you're going to have B bar, because it's 0. And you're also going to have C. So you're going to have B bar, C. Okay, and then you have this lonely mini term here that still has 3 inputs. But the whole point is to wrap around in a circle, in a cylinder this way. Okay, here's something a little more complicated. 7-segment LED for the digits 0 and 9. You're going to actually use this in the experiment next week. So here's a 7-segment display, can display any 0 to 9, any of the digital decimal numbers. And F is an LED that will light up when you have certain numbers. Well, for 1 would have these B and C lit, so F would not be lit. Number 2, you would not have F lit. Number 3, you would not have F lit. But number 4, to make a 4 here, you would have F lit. That little LED there. So for 0, 4, 5, and so on, you want the F to light up. Okay, this is called binary coded decimal. Anytime you're converting decimal to binary, or vice versa. BCD, binary coded decimal. So for these digits, 0, 4, 5, these decimal numbers, 0, 4, 5, 6, 8, 9, you're going to have the F LED lit up. Okay, so here's the truth table. A, B, C, D, you have 4 inputs, and these colors represented, these colors here. So you approach this as, well, here's 2 that are adjacent, and here's 2 that are adjacent, and here's 2 that are adjacent. So if you take these 2 that are adjacent, you can see that it doesn't matter what D is, D can be 0 or 1, so D is going to drop out. You can take these 2, and you can see that doesn't matter what B is, B can be 0 or 1, so B can drop out. And you can take this one and this one, or you can take this one and this one. You can take the 2 greens together, okay, because you can wrap it around the other direction. You can wrap it around this way so that this edge would meet this edge here if it were wrapped around. So this one would be adjacent to this one. And so for the green one, you can see that, well, A has to be A bar, B has to be B, A bar B. And then if you look over here, you can see that C can be either 0 or 1, because you have this or this. So C is going to drop out, and D is going to be 0, so D is going to be D bar. So you have A bar, B, and then D bar. And that's this for the green ones. Okay, any pair. And you can use pairs over again. You can use a number over. You can use any mini term over again. Okay, here's another example where you're trying to do math with it. You want to know something, you want to do a conditional operation. When is AB, a digital number, less than CD? Okay, so if AB is 0, C and D can be 1, 2, or 3, right? Because 2 digits here, you can only get up from 0 to 3. If AB is 1, then CD can be 2 or 3. When AB is 2, CD can be 3. So here's 0, 1, 3, 2. And you can write this truth table. And when AB is 0, you can see that C and D can be 1, or it can be 2, or it can be 3. And so you you get all these combinations, all these mini terms. So the block of 4s, you can take a block of 4 now, a block of 4. Okay, so you can see here, if you take this block of 4, first look up here. It doesn't matter what A is, A has to be A bar, but B can be 0 or 1, so B is going to drop out. And then for these 4, you can look over here, C has to be C, and D can be anything, so D is going to drop out. So you're going to have A bar C, A bar C for this 4. Okay, so you've already taken care of 4 of the mini terms with just 2 letters. So if you're designing a circuit, that's very important. That's very important. Okay, and then you can take this green one and this, then you can take the ones in the first column. So remember, you use these 4, but you can use this one again. You can use this one and this one together. And then you can also use this one and this one. So you use this mini term 3 times, once for the block of 4, once for this block of 2, and then again for the block of 2 for here and here. So you've gone from 1, 2, 3, 4, 5, 6 mini terms that had all these different inputs, 4 different inputs, and you reduce them to 3 terms. 2 of the terms have 3 inputs, and 1 of the term has 2 inputs. Okay, so here's digital circuits. First thing you're going to do is measure where does the gate turn on and off? What voltage? So you're going to put in a variable voltage, then you're going to measure its output with an LED and a current limiting resistor. Then you're going to look at truth tables for various gates, and these are these are unknown gates. So you're going to see what the gates are, what the inputs and outputs are, and then determine which gate it is by that. Then you're going to construct an XOR gate using only these 7400 NAND chips. So you're going to take only NAND gates and make an XOR gate. And finally, you're going to design and construct a 4-bit decoder. And that's shown on the next page. So you're going to take these 4 bits, A, B, C, and D, where D is the least significant bit and A is the most significant bit. And you're gonna make it so when you have certain number coming in, it's going to light an LED. So when the decimal numbers 3, 9, and 11 are high, then the output's going to be high. So here you have 0, 0, 1, 1. 0, 0, 1, 1 is 3. So that's a mini term there. 0, 0, 1, 1 is a mini term. And then you can fill in all the rest. You can fill in what 9, what 11 is, and so you're going to get basically three mini terms, and you can write an equation for that and simplify that. And then you're going to make the circuit. Make the circuit that does that. You're going to have to design a circuit. So for those of you who are not coming into the lab, you can use logically, which is in the lab directions, and then you can design the circuit there and take a screenshot of that and then put that in your lab report. Okay, so this is 3, 9, 11, not 13. I'll change that. Okay, that's it for today.